All right, so we're going to talk about QR factorization, orthogonal matrices, and projections. Last time we had a few problems on QR factorization without going through it. And I think it's a good idea to have an explicit example on what it is. So the goal of QR factorization is to write any matrix as a product of two specific matrices. So this R right here is going to be upper triangular. And this Q is going to be what we're going to call an orthogonal matrix. All right, the key with all this is this factorization is going to encode the Gram-Schmidt process. So the Gram-Schmidt process, this is just the fancy name for finding an orthogonal basis. Not just an orthogonal basis, an orthonormal basis. So last time we focused on how to find the basis, but now the key takeaway is that process also gives you a way of decomposing a matrix into two parts. And we're going to learn more about these two parts later on. All right, so in order to do this QR, what we're going to do is we are going to decompose these vectors and change them into an orthogonal basis. So let's go ahead and do that. So we're going to take these two vectors right here, and we're going to convert them into an orthonormal basis. So just to draw a picture, what's happening right now, we have one vector that looks like that. That's 1 minus 1. And our other vector, this 2, 3, looks like this. And those aren't quite orthogonal, and they definitely aren't normal. And so we want to convert them into an orthonormal basis. And in doing so, what we're going to be able to do is we're going to decompose this matrix 1, 2, minus 1, 3 into a QR factorization. So let's just focus on decomposing this matrix, and then we'll recover how exactly that factorization works. All right, so this may be a recap from last time, but that's okay. So we're going to start with our original vector. We're going to pick one of them. Let's just pick minus 1 and 1. And ordinarily we project away all the previous vectors, but there are none. So we're just going to, instead, all we're going to do is we're going to just divide by the norm. And so we get that our first basis vector is just 1 over square root of 2 minus 1 over square root of 2, because the norm in this case is just 1 squared plus minus 1 squared square rooted, which is square root of 2. So we divide everything by square root of 2. So the first one's easy. And this is going to help us build our Q. So that Q, as it turns out, these vectors are going to create the columns of our Q. All right, now we go on to the next vector. So that was our B. Now we're going to go on to the next vector. So we had V2, which was 2, 3. And now we're going to project away. And now we have a vector to project away. So now we can compute this intermediate vector, which is the original vector minus the previous projection. There's a minus right there. And this is going to give us 2, 3 minus a lot of arithmetic here. Now, one thing I want to emphasize is this arithmetic is really encoding a matrix. So this part right here, this part is actually a matrix, and we're going to make a bigger deal about that later. It turns out to be very related to Q. But to compute this, what we're going to do is we're going to evaluate those parts. So in this case, we get, this is 2, 3 minus the vector times minus 1 over square root of 2 over 1, or just 2, 3 minus 1 over square root of 2 times the vector. And I'm going to leave it like this for now. We're going to need that later. But for now, let's go ahead and let's simplify it. So we get 5 halves and 5 halves. All right, so that was just what 2, 3, the 2, 3, when you project away gives you this. And now what we want to do is we want to go back and we're going to divide by the norm. All right, in this case, the norm is the square root of 5 halves squared plus 5 halves squared. So that gives us 5 over square root of 2. So that's what we're going to divide by. And when everything's said and done, we're going to get 1 over square root of 2, 1 over square root of 2. All right, so that's our second vector. All right, so now what's really nice is that this vector right here is going to become part of our Q. This Q, all this Q does is encode our orthonormal basis. This is the Q. So just encodes that orthonormal basis. So this gives us the Q right away, which is really nice. But how do we get this R? So this R is determined by the work that we did. So let's go back and recover it by making a few observations. So right here, in this step right here, we have that 1 minus 1 is equal to square root of 2 times 1 times the first new basis we had. Right? Because what did we do? How did we get from 1 minus 1? How did we get from 1 minus 1 to our basis? We divided by square root of 2. So this is what we get here. And we can play a similar game with the other vector. So how do we do that? Well, we got that this projection right here, this was really 5 halves, 5 halves. But that 5 halves, 5 halves was really our basis vector times some multiple. So times this multiple here. So this is really just 5 over square root of 2 times our basis vector. And so this, if we take that right there, we can use that to solve for 2, 3. So this one's going to give us, we're going to solve for 2, 3 right here. Put this on the other side. And we get that 2, 3 is equal to 1 over square root of 2 times our first basis vector plus 5 over square root of 2 times our second. Okay, so we can write, let's write them in order. So we had that one. We also had 1 minus 1 was equal to square root of 2 times first. That was from before. So then the very first one, we divided by square root of 2 plus 0 times the second. Okay, so we're almost there. So it turns out that the R matrix is encoded by just these extra coefficients. So this was the first one, and this was the second vector. And so these coefficients right here are going to encode your R. So I contend that we can take R to just be the transpose of those coefficients. So altogether, we have that Q was this matrix, and R was this one. And if we multiply these together, let's just multiply these together to make sure we get what we wanted. We multiply that one times that one, we get 1. And if we multiply those two, that's a little harder to do. We should get 3. We get 2. Oh, this should be a minus. That's why. That's a minus. All right, this should be a minus. There's a double minus here, so that should be a minus, which means this should be a minus right here, which gives us a 2 for that one. All right. All right, found the mistake. We're going to go on to the next one. It's going to give us -1. And finally, we can do the last one. When we multiply those two together, sure enough, we get 3. That's exactly what we wanted. So that's how we do QR factorization. So the main idea is just to follow your work and carefully keep track of the coefficients of the original vectors in terms of the new basis. So just for emphasis, the ones on the diagonal are going to go there, and you're going to transpose the other ones. So why does this work? What makes this work? Well, if we take this Q and this R, we can actually think of matrix multiplication in a new way. So that's kind of the key why this all works. So let's go over why this matrix multiplication seems to work. So this is a 2 by 2 by a 2 by 2. So altogether, we're going to get a 2 by 2 matrix. And the key is that if we view this first matrix as just 2 vectors, right? In this case, we can view them as, say, B1 and B2. Then it turns out you can write the first column of A. You can write this one as B1 times this R. Sorry, not that one. Times just this one. Plus, you can write B2 times this one. So this is another way of kind of thinking about matrix vector multiplication. You can, instead of getting an individual entry, this vector right here, this is an entire vector, you can view this as a linear combination of the columns of the first matrix times the first, using the column of the second matrix as the coefficients. So that column is right here. Those are the coefficients. And if you check this out, this actually works. So this is the reason why this works, is because we're expressing the columns of the result as linear combinations of the first using coefficients of the second. And that's exactly what QR factorization does. All right, so that's an overview of QR factorization. Let's talk about this Q matrix. So this Q matrix has some important properties. It turns out this is an orthogonal matrix. And so what are some important properties of this matrix? So this right here is an example. So let's just use this as a running example to figure out what makes a matrix orthogonal. So we got this matrix because we formed an orthonormal basis. So it's columns. An orthonormal basis. This means many things. So one is that means the norm of each column is 1. Right. We also have that if you dot or take the product of two of these, you have to get 0. They have to be perpendicular. And they have to span all of Rn. They have to be a basis, right? And so this is also saying that they're all linearly independent. So this is a 2x2 example, but we can check these out. So we got the first column, if we want to take the norm of that, right? What's the norm of this? We get 1/2 plus 1/2, which sure enough is 1. Square root of 1, which is 1. So we got this one, and the other one's the same math. These are perpendicular. We can check that out as well. So here we're just doing the same multiplication, except one's going to be the same sign, and the other one's going to be the opposite sign. So this is going to give you 0, which gives us this one. And we can check that these are in fact linearly independent. In this case, it's a 2x2. So the only way they can't be linearly independent is if they're multiples of each other, and this pesky minus gets in the way. So this is an orthogonal matrix whose columns form an orthonormal basis. So that's what this is. So why is this important? What makes this important? Well, let's actually look at this basis. So if we look at this basis is going to look something like this. And if we extend this, this is now a square grid. So this is going to form a square grid. And so in some sense, every orthonormal matrix, every orthogonal or orthonormal matrix is a change of basis matrix. To an orthogonal basis, or from rather, to or from. Actually, it's actually an orthonormal basis, just for emphasis. So that's the way we should think about what Q is doing. So if we do use the before and after graph, right, we take Q, right? Q is just going from the standard basis, and it's transforming it into some other orthogonal grid. And so in this case, it just happens to be a rotation. That's what Q is going to do. So every orthogonal matrix is just taking the standard basis, is just taking, in some senses, taking the circle, and it's just keeping the circle as a circle. In fact, if you actually traced out every single thing on this circle, you'll get the same shape. It may be flipped around, but it doesn't change. So one key thing about Q, geometrically, this orthogonal matrix, this orthonormal matrix, doesn't change any shape. In the before and after graph, it only rearranges it. So that's what it's doing geometrically. And you can think of this as a change of basis between orthogonal bases, orthonormal bases. But one other key property, which is really cool, is this one. The inverse of Q is equal to its transpose. And this is what really makes it shine, because this is a very special property. There's not very many ways this happens. Those mean very different things. The inverse and the transpose mean very different things, but in terms of orthogonal matrices, they actually give you the same thing. All right, so why is this? Let's just give a quick explanation. And I'll just do it in a picture. This is best done with pictures. So here you have all these basis vectors. And we're going to multiply them. And this is going to be Q, and this is Q transpose. And we're going to multiply them. And if they're inverses, then this should be the identity. So we're going to compute this one at a time. But Q transpose, now that first B vector is going to be right here. Second one's there, and the third one's the last one's all the way on the bottom. All right, so now when we compute this, if we're on the diagonal here, we're going to dot those. So that's just the dot product between a vector with itself. And we know that this is just the norm of that vector squared, which is, we know this is the 1. So that means we're going to have 1s on the diagonal. This applies for any of the same ones. So when you dot the same vector with itself, you're going to get 1 because the norm or length is 1. On the flip side, if you take two different vectors, so if we take two different ones, say I take those two, well, these are perpendicular. And because they're perpendicular, we know that you're going to get 0. And so this applies for any two different ones. So altogether, you're going to get 0 all off the diagonal for the same reason. And this, sure enough, is the identity. So that's an important fact for orthogonal matrices. And the last important fact, which is actually pretty important, is about partial orthogonal matrices. And that is that if you take say this is, we're going to call this Q, but this is going to be partial. This is going to be just maybe it's 3. Maybe it's 3 vectors in Rn or any number. Yeah. And if I take this and multiply it by its transpose, this gives you a new matrix called P. And this P is very special. This is the projection onto the span of those vectors. But this only works if those vectors are orthonormal. So the orthonormal is important for creating these matrices. So this is the projection matrix onto the space generated by those. So let's go up and just go back to the point we made earlier, which was when we did this projection right here, I emphasized that this was actually a matrix, right? So what's really going on here in this context is we really have what's the projection onto this? Well, this is just a line. You're projecting onto the line 1 square root of 2 minus 1 over square root of 2. You're projecting onto this line, and the projection matrix is simply taking a partial matrix of Q. In this case, it's just a single vector and multiplying it by its transpose. And this gives you the projection matrix, which is exactly what you see right here. So let's do a different example. All right, so let's test this out. So we're going to test out this matrix on a larger example. So let's go ahead and say, what is the projection matrix? Onto the span of 1, 0, 0 and 0, 1, 0. Okay, so for emphasis, this span here, this is just saying the set of things you can get with adding those vectors together, but more colloquially, z is equal to 0. All right, so if you want to project onto the set of vectors where z is equal to 0, intuitively we know that p just zeroes out z. And that means x is the same, y is the same, z gets zeroed out, you don't mess with anything else, and we should end up with that one. But on the flip side, if we want to use our newfound idea of using an orthonormal basis to find the projection matrix, we can write it like this. We can take our partial Q, multiply it by its transpose, and sure enough, what's going to happen here? What's going to happen? We get 1 there. And in fact, on all the diagonal ones, we're going to get 1. We can keep doing this. Except that last one, we're going to get 0, just like we expect. All right. And now if we do any of the off diagonal ones, we're going to get 0. So our P, in fact, this idea works. And this works for any subspace as long as you have an orthogonal basis, an orthonormal basis.